In the first 3 videos of this series, which you should have watched before arriving at this video, we looked at the multinomial coefficient. We looked at how we could use that coefficient to construct a multinomial distribution. And then we looked at how we could use that distribution with our observations to determine how closely those observations fit with what we expected given the parameters of the multinomial distribution. This was all leading up to what we're going to look at now, and that is a goodness of fit test. Here are the conditions and the steps. First, we will select a random sample of participants. Each observation must be independent of other observations and result in assigning the participant to one of k categories. As we've discussed before, those categories need to be mutually exclusive. You can only put an individual into one category, and they must be exhaustive. That is, they represent all the categories in which you can place the units you are observing. The response probabilities, the probability of being assigned to a category, must remain constant and be the same for every observation, which will be the case if we randomly sample from our population. We hypothesize the probability of assignment to each category. So here is a null hypothesis that the probability of being in category 1 is equal to some value that we decide on. The probability of being in category 2 is also equal to some probability that we hypothesized, and so on all the way up to the kth category, in which the probability of being in category k is what we hypothesize for category k. The symbol here between these different categories is the intersection symbol, meaning that all of these have to occur at the same time. That is, the null hypothesis is that all the probabilities we specify for all of the categories are correct. Construct the multinomial distribution using these hypothesized values, and then determine the rejection region based on the largest values of the goodness of fit statistic, keeping our alpha prime, that is our actual type 1 error rate, less than or equal to alpha, our nominal type 1 error rate. Reject or retain the null hypothesis based on the goodness of fit statistic. That is the statistic that we actually calculate based on the observations we make. Let's look at an example. A virus persists in 3 variants, A, B, and C. 1 year ago, a large sample study estimated that 50% of the infected population were infected with variant A, 25% with variant B, and 25% with variant C. A public health researcher randomly selects 4 infected persons to test the hypothesis that the variant distribution is still the same as 1 year ago. So our null hypothesis is based upon 1 year ago, when the probability of variant A was 0.5, that of variant B was 0.25, and that of variant C was also 0.25. Let's suppose we are doing a small study. We select at random 4 infected individuals, perhaps do a blood test, and determine what variant they were affected with. Given that the sample size is so small, let's go ahead and allow our type 1 error rate to be 10%. Suppose these are our observations. We end up with 3 in category A, 1 in category B, and no one in category C. Our goodness of fit statistic is 1.5. Here is the multinomial distribution. Note again that this distribution was created using the null hypothesized values for pi1, pi2, and pi3, and a sample size of 4. Those are the parameters of the multinomial distribution when you have 3 categories, the 3 population proportions, and n. In addition to giving the probabilities, in the 5th column, I am showing you the cumulative probability, starting with the highest goodness of fit value. That is in the 6th column, and I have sorted all the arrangements of A, B, and C based upon the goodness of fit statistic. The highest value of the goodness of fit statistic is 12, and the lowest value is 0, the lowest value indicating that we have a perfect fit with what we expected under the null hypothesis. Now that we have calculated the multinomial distribution as well as the goodness of fit values, and sorted the distribution based on those values, it's time to form our rejection region. We begin forming that rejection region by looking for the worst fit, the lack of fit, and that would be with a goodness of fit statistic of 12. We have 2 of those, so both of those will go in our rejection region. We'll continue down in this fashion, moving down to 6 and putting 2 6s in our rejection region, and so on, until we finally reach a cumulative probability that would take us over our acceptable type 1 error rate. We set that at 10%. When I look at this, I see that the first cumulative probability that is over 10% is 0.101. That is associated with a goodness of fit statistic of 5.5. But note there are 2 5.5s. I can't put one of those in the rejection region and not the other, so neither of those will go in the rejection region. Putting both 5.5s in our rejection region would give us a cumulative probability of 0.10156. That is over 0.10. Therefore, my critical value is 6, and I'm going to form my rejection region with values of 12 and 6. My goodness of fit statistic is 1.5. That is nowhere near my rejection region. In fact, a value of 1.5 for this particular arrangement that I found of 3 in category A, 1 in B, and 0 in C has a cumulative probability of 0.50. So I will not reject the null hypothesis. Does that mean that we can conclude that the variants are in the same proportions as what we observed a year ago? Not at all. It just means that we do not have enough evidence to reject this null hypothesis. And remember, my sample size was quite small, so I did not have much power to detect any differences from a year ago. I might want to consider doing a large sample. But if I do a large sample, that's going to make my multinomial distribution very difficult to construct. How do we handle that? I suggest that we move on to the next video and learn how to conduct a large sample goodness of fit test.